Alright, so yesterday we looked at probably the easier parts of sketching a titration curve. Not to say it was easy, but they were the easier components. We're going to look at the hardest part now. Can you please make sure you have a calculator out, because I'm going to rely on you to do the maths for me, please. At the equivalence point, this is where the reaction between the acid and the base, not the acid and water, and not the base and water, so not dissociation, this is where the reaction between the acid and the base is complete. How do I show that a reaction is complete in a chemical equation? An arrow. Okay. So in this reaction, I started with, and I'm sorry I'm not going to use my states of matter here just for speed, but CH3COOH, and I reacted it with sodium hydroxide. As you've told me to, I do a full arrow. The products of this are sodium ethanoate, or actually because it's aqueous, sodium ions, ethanoate ions, and water. Okay? Now, this last bit is really, really important because ethanoate ions have the ability to react with water to make an alkaline solution. Being the conjugate base of a weak acid, it is going to be alkaline in nature. So then sodium is going to have no effect, by the way. No effect from the sodium. These two can go on to further react and change the pH. This is why this salt is not neutral. It's called a neutralization reaction because water is made, but the result is not neutral. And if I look at my sketch, it's going to be somewhere between 4.7 and 3.7. Well, halfway between that is not 7.0. So it's about 9. So I know that it's not going to be, if my final answer is 7, I know I've got a mistake. Okay? These two species no longer exist. That's what the arrow means. They're no longer present. Well, it's kind of a little lie. This one is, but not from the initial solution. It's no longer there. Okay? However, because they've reacted, there's some work I have to do using some level 2 chemistry here. Okay? And I'm going to do it just with I'm going to try and keep the maths really simple for you. How many mils of this did we use? 20. Okay? And how many mils of this from our equation, because they're the same concentration, how many mils of this did we use?
Also 20.
Another 20. Cool, because they're the same comp. If I have 20 mils plus 20 mils, and I assume that the densities of both of them are the same, it's an assumption you have to make in this, okay? Otherwise it's too hard. Then what would I expect the total volume over here to be? 40 mils. Okay, great. That's really important because without knowing that there's been a change in volume, I'm going to make an incorrect assumption about the concentration of that ion. Okay? Our concentration for each of these was 0.450 moles per litre. Sorry, I'll use shorthand for this one. Okay? So therefore, if I look at my balanced equation, rewind. So from this I can find my number of moles, N equals Cv, which we did in an earlier step when we were finding our pH of our, sorry, it wasn't that one, was it? When we were finding our volume for our equivalence point, we'd already done this step, okay? And we found that it was 9 thousandths was our number of moles, okay? So it was, and because everything's in a 1-to-1 ratio, that's going to be true for all of them. So it's going to be true for our ethanoate ion as well, because I can't create something from nothing. Okay, it's just a chemical reaction. It's not fusion or fission or anything like that. So if these are 0.009 moles, then each of these two, disregard the water, it's always about 56 moles per litre. These two are as well. Sodium's irrelevant because it's not going to undergo any reactions. Now, again using my level 2 maths or equations, I've now got a new volume, 40 mils of solution. I've now got the number of moles of the ethanoate ion. This means I can work out the concentration of that ion. And it's not going to be 0.45 moles per litre. It's going to be half of that. So 9 over 40 times 1,000. Yeah, that's right. So, and I've got the mils. So we're going to end up with 9/40ths. So it's going to end up being 0.225 moles per litre. This is the step most level 3 students forget. They dive straight into the hard maths without doing this important step and therefore miss out on the excellence for it because they haven't adjusted for the new concentration. Okay? And therefore they get confused by their answer being out by so much. Alright? So, we did an easy one because it was the same volume and it was the same concentration. Okay, but the key thing is no matter what we did here, these number of moles would be the same. So the number of moles there would be the same as there, would be the same as there. What might be different in your question is the volumes. It might be 50 mils, it might be 70, it might be 25, something like that. So just make sure you do the calculation. So go through that slow process. Okay, so that's our first step. We found, the first thing was we find concentration of the important product, which is the one that's going to dissociate with water. And that's that. Okay, so that's our first really important step, often forgotten by most students whose work I've marked for this. Okay, where they go straight into the next step, forgetting this, and just use the 0.45. Right, the things I put the box around, they are going to become the basis of my next step. I know that this is a conjugate base, so I know that I'm working with a weak base question now. Okay, so the next thing I'm going to do is I'm going to write that equation again, but this time starting with the two things that I've put a dashed box around, because this is a chemical reaction that can occur as well. Now, if this is the conjugate base of a weak acid, is this going to be a full reaction or an equilibrium? Equilibrium, cool. So weak bases also only partially dissociate. So, here goes. And again, apologies for not using states of matter, but I'm in an exam and I'm trying to do it as fast as possible. Okay, we noticed that OH minus has made what we'd expect, because we know it's an alkaline salt. We've looked here and it's above 7 in our sketch, so we know it's going to have hydroxides. Darn it, these are really hard questions. Okay, we were given a Ka, a pKa. We need a Kb for this because it's a Kb expression. So that's my first thing. Now, remember I said that there was none of this present, or none of it left over. Okay, there's none left from here. So the only ethanoic acid that you've got in this solution is caused by this reaction here. Therefore, you can make an assumption that these two are the same. Okay, so you're now back to doing a weak base calculation. You know this one here is 0.225 moles per litre, so we're good there. What we really need now is a Kb expression and then a Kb calculation. Okay, this is where you just have to remember a lot of your maths, okay, or a lot of your relationships between things. So if I've got a Ka of 10 to the negative 4.76, Kb equals Kw over Ka, which equals 10 to the power of negative 14. So remember that magical number? pH is 0 to 14 scale, which is slightly lying, but pOH and pH add up to 14 at standard conditions. That's where that 14 comes from. Okay, it's Kw. pKw is 14. Divided by 10 to the negative 9, sorry, I couldn't answer, 4.76. And if we're good at it, we shouldn't need a calculator for this. It's 14 minus 4.76 for our exponents. 10 to the negative 9.24. So I now have the Kb for ethanoate ions. Now my next thing is to put some things, and you'll notice I've used X, you might want to use S, A, B, it's up to you. When I do algebra, I like X's, Y's and Z's, and W's if I'm doing a really evil one. It's your choice. I'm going to do X because I find it easy. I'm also going to know that X is hydroxide ion concentration because I'm going to need that for pH later. Okay, so now I've got my 10 to the power of negative 9.24. So I've got this number here. I can use that. So I'm going to rewrite KB as an expression, but I'm going to plug some numbers in as I go, so if it's too fast, slow me down. KB, 10 to the negative 9.24, equals these two times each other, the concentration of, and that x. So I'm going to call it x squared, the same thing times itself. Divided by these. Well, I disregard water because there's water present on both sides in reality, because these would be aqueous. So over 0.225 moles per litre. I rearrange this. And I'm going to use brackets in my calculator just to make sure it doesn't do a syntax error or something like that. So I go square root of bracket 10 to the power of negative 9.24 times 0.225 close bracket equals. This is where I need you to be wonderful, please.
1.14 times 10 to the negative 5.
Okay, please don't get rid of that number. I need that. This is my hydroxide ion concentration. Okay, here's where we need to remember another relationship. That wonderful KW is coming in yet again. Same number. If I need to find hydronium ion concentration and I've got hydroxide, then I go KW over hydroxide. So the actual relationship is KW is calculated by going hydronium ion concentration times hydroxide. So I'm just rearranging that one to make hydronium the subject. So I can put some numbers in there. 10 to the power of negative 14 divided by, hopefully I didn't take it out of my calculator, I'll just press the answer button. Okay, much easier way to avoid mistakes. But in my exam paper I write that down. Okay, but I use answer in my calculator. And I get a number there.
8.79 times 10 to the negative 10.
Okay. Well, this is cool, because now I've got an easy bit of work to do. pH equals what to that?
Negative log.
Negative log. Okay, so now I'm at pH equals negative log of this. Which equals
9.06.
9.06. Brilliant. Which looks about what that would be, and I said it started with about 9, didn't I? So you can't just take the difference, halve it, and you've got it right. But that's close, so it's a good estimate. Sorry? You look, it is. That's why we sketch it to start with. You can go, oh, well, it's going to be, it kind of looks halfway between the buffer zone and the final pH. So if I halve that, it should be near that. It's just like when you're in physics and you go, well, I expect the answer to be in the magnitude of 10 to the power of 5 or in the magnitude of 10 to the minus 3. You want to have a ballpark figure. So guessing, it's an educated guess because you've sketched it using some good maths. An educated guess is a really good idea. So, you know, yeah, that looks realistic. I'm not going to proof check everything now. I'm going to move on and I'll proof check my maths once I've done all 3 papers. Okay, so it is a guess, but it's a good guess that it's going to be around about 9. Okay, any questions about that? That is the whole process. There's just, you can see there's so many types of steps in it. That's what makes it hard. It's not the getting the answer, it's getting started. It's hard. All right, so just, no questions? I'll just rewind the steps because then you can go to the end of the video and just look at the steps, maybe as the first thing. Step 1. Balanced equation at equivalence point, which will be an arrow. So these two things don't exist anymore. From step 1, you can find the concentration of the important product. In this case, it's the ethanoate ion. It might be the ammonium ion. It might be ammonia. So it'll be a conjugate base or acid. Okay. Step 2. Show that important thing you've worked out the concentration of dissociating with water, because that is going to happen at the equivalence point. If it's an acid, this is a dottle. It won't be. It'll be a base. Okay? So If it's a base, you need to realise that it's going to have hydroxide made, so you're going to have to work out Kb. So there's going to be a couple of steps that involve Kw to find things out. So find your Kb, write your Kb expression with this assumption, solve for hydroxide. Then your final step is to solve for hydronium, which will give you your pH. Alright, it's about learning the steps for these ones. Yeah.
Why do you have to find hydronium?
Right, pH you can't find from hydroxide alone. Okay, so pH is sort of shorthand for pH3O+. So it needs to be H3O+ that you're working with. Good question. Yep.
If you went and figured out PLH and then went to pH.
14 minus that. Equally valid. Just show that you're doing that. So what you're using is pKw, that's the 14. So state that. pH equals pKw minus POH. Actually be explicit and state that. Just in case you make a silly mistake. It'd be horrid to make to drop a grade because of a silly mistake that one line could have explained and allowed you to get credit for. Okay. Anything else there? Well done.